Problem 3. In part A, I have a right triangle, so I can find the missing side using the Pythagorean theorem. The missing side is the hypotenuse, so I'll start with 4 squared plus 6 squared, those are the two legs, equals the hypotenuse squared. That gives me 16 plus 36 is x squared, or 52 equals x squared. I can solve for x by taking the square root of each side. I don't need the plus or minus because I know I have a positive value. And so there's my answer. X is the square root of 52. However, I do want the exact simplified answer. Are there any perfect squares that go into 52? The answer is yes. 4 goes into 52 13 times. The square root of 4 then comes out as a 2, leaving me with 2 times the square root of 13. In part B, the missing side is one of the legs, so I can write x squared plus the other leg squared equals the hypotenuse squared. That gives me x squared plus 9 equals 81. When I subtract 9 from both sides, I get x squared equals 72. I can solve for x in that same manner, square rooting each side. Can I simplify square root of 72? Well, I'm always looking for the largest perfect square that goes into that number. In this case, it's 36. Square root of 36 comes out as a 6, and so my final answer is x equals 6 square root of 2. What if I hadn't thought about the 36? What if I had only noticed, say, that 9 goes into 72 8 times? Well, then I just have to keep going because there's also a perfect square in 8, namely 4 goes into 8. Square root of 9 is 3, square root of 4 is 2. The other 2 would get left behind, and you can see there again is the 6 square root of 2. Problem number 4. In part A, I have a 45, 45, 90 triangle. I would like to write down the measurements of the other two sides. So I do have this leg given. There's a hint that because this triangle is isosceles, meaning these two angles are the same, therefore the two opposite sides are the same. So right off the bat, I figure out that the x value there must be just another 5. To get the y, I can use the Pythagorean theorem. I have 5 squared plus the other 5 squared must give me y squared. That's 25 plus 25 is y squared. In other words, y squared is 50. Y must be the square root of 50. Can I simplify that? Yes, I can, because 25 is a perfect square that goes into 50. And so I end up with y equals 5, square root of 25 is 5, times square root of 2. Here then are the final answers. You might remember that every 45, 45, 90 triangle follows this same pattern. The two legs are the same, and the hypotenuse is square root 2 times as much as one of the legs. In part B, I have a 30, 60, 90 right triangle. I have the smallest side given as 7. I know it's the smallest side because it's opposite the smallest angle. I'm trying to find the medium side, the one across from the 60 degrees, and the hypotenuse, the one across from the 90. Now, a 30, 60, 90 triangle is exactly half of an equilateral triangle. An equilateral triangle is one where all the angles are 60s and all the sides are the same. Well, you can see here that this 7 is exactly half of this entire side, which means this entire side is 14. But if all the sides of an equilateral triangle are the same, that makes this 14, and importantly, it also makes this h 14. So I have an h here of 14. How can I find m? Well, I can use the Pythagorean theorem. It is one of the legs, so I would have 7 squared plus m squared equals 14 squared. I'm using the original right triangle that was pictured. This is 49. This is 196. I can subtract the 49, and I obtain 147. Once again, I'll square root each side. Now, this is a bit of a tougher one. How do I find factors of 147? Well, it's not even, so I know 2 doesn't go into it. Let me add up the digits. 1 plus 4 is 5 plus 7 is 12. Aha, 3 goes into 12, which tells me 3 goes into 147. And if you divide this on your calculator, you will discover it's 3 times 49. And that's great news because 49 is a perfect square. So I can split this up. 49 times 3, the square root of 49 comes out as 7. And so here's the final answer for m, 7 square root of 3. You might remember again that every 30, 60, 90 triangle follows this same pattern. Whatever the shortest side is, in our case it was 7, the hypotenuse will be double, 14, and the medium side will be square root of 3 times as much as that shortest side, so 7 square root of 3. Problem number 5, rationalizing the denominator means rewriting it so there is no radical at the bottom. The trick is to multiply the top and bottom by the square root you're trying to get rid of. Root 2 times 1 is just root 2. Root 2 times root 2 is root 4, which simplifies to 2. And so I have rationalized the denominator. Here, the trick would be multiply top and bottom by root 3. I'm going to get 2 root 3 up top. Root 3 times root 3 is root 9, which is just 3. Here, I'll multiply square root of 5 over square root of 5. That gives me 10 root 5 up top. Root 5 times root 5 is root 25, which is just 5. This time, I do have some simplifying I can do at the end because 5 goes into 10 twice. I can't touch the 5 on the inside of the radical there. This isn't even a fraction. I end up here with simply 2 square root 5.